Welcome to another episode of Coffee with Samso, where we talk about mineral resource stories with identities or companies. Today I've got a different tack. I've got Ryan Noble here, is the principal research scientist from CSIRO, talking to us about some unique sampling methods that are being used sort of in the industry. Welcome, Ryan, and maybe introduce yourself, what you are.
Yeah, thanks for having me. As said, I'm a research scientist primarily in CSIRO. I also manage a group of people as well on quite a diverse range of projects, but we work with the Discovery program, and really it's all about bringing value and applied science to industry to discover more resources for Australia. That's our primary focus. We stretch across a range of different commodities and a range of different sciences, so geophysics, geochemistry, which is where I'm primarily based, and particularly in the regolith space, so the soft rock and the soils, and we have others that work in the hard rock space and some of the characterization, instrumentation, and a range of other fields. But my focus is really anything above the hard rock interface, and for me, and one of our big goals of CSIRO research is how do we explore better through cover, which is a major challenge for most of the mineral exploration explorers in Australia in particular. So we work with techniques, whether it's collecting soils or eucalypt leaves, for example, right down to groundwater and better information from drilling materials, and how do we interpret that better. My focus has been on soils and groundwater primarily in that space.
Okay. Obviously, I sort of got to know who you are and what you are through my interviews with Moho Resources, and we've talked about how they've got this unique sampling method with the Empress Springs project in Queensland. It's intriguing because in this day and age, it's about vectoring and targeting at the most efficient. And in a world of mineral explorers, we don't normally have a lot of money, and being wise in how you spend that money is going to be the critical part, I guess, for you guys.
Yeah, the Moho engagement was a really interesting one in terms of we had an early discussion with how do we make the most efficient use of our exploration in that area. Obviously, they have some really interesting targets but a huge search space, and so we sat down and sort of talked through a couple of things around what are the best options for them, and in the setting around Empress Springs, they had upwards of 30 to maybe even up to 100 metres of cover, but 50 metres of cover was pretty consistent. And so early on we were sort of ruling out probably soil sampling is not really a great technique, regardless of the various options you have. And what we settled on was possibly using hydrogeochemistry. So, the idea is that the water table in that area might be 10, 20, maybe even 30 or 40 metres down, but that water is moving through the rock environment, and it's interacting with those materials, and essentially it's picking up a signature. So when it interacts with mineralised rocks, it tends to get more of those elements in solution. And so by sampling the groundwater, we're actually able to get a better, more representative sample of a larger area. And so it's not necessarily going to pinpoint the exact deposit, but what it means is you can, close in your search space much more rapidly. And so it was the idea with Moho was that we would collect a large number of samples from across their tenements, and then look at the chemistry within that to possibly identify smaller areas where you would do more detailed work. And so that's where we are in that project. We've just sort of they've collected the groundwater, so it was a nice interaction in many ways. The COVID thing made a bit of a challenge where we couldn't necessarily travel between places, but we were able to train them in the techniques that we use, and then collect really good representative groundwater samples from that area.
So when we talk of groundwater, you're talking about from bores, existing bores, and then how do you vector, because the water's moving, how do you do the vectoring?
So it's real. There's a couple of different things, and it is collecting mainly bore water and farm wells. And this came out back in the early 2000s. I think we were doing more detailed work around drill holes into sulfide ore bodies. And what our biggest challenge was, we'd get all these unusual chemical signatures in the groundwater. You know, we get platinum, palladium, big nickel signatures in the groundwater, but nearby we'd get less concentrated, even though we weren't very far away. And then the big challenge we had was, well, what does actually a background groundwater look like? And that was when we were driving around the northeast Yilgarn and happened to see a couple of farm windmills on the side of the road and jumped out and collected them. And that sort of...
As you do.
Yeah, as you do, wandering around. And then we started going, well, hang on, these farm bores are often spaced about 5 kilometres apart. So that's a great consistent sampling medium, or grid almost, across a large area that we can collect. And so that's where we went to next. And then so once we've built up that database of groundwater, all of a sudden those areas that we weren't sure how anomalous they were in the drilling ore bodies and things like that stood out like Christmas lights in the background. And so from there we were able to then adapt that into other areas. So now on the regional scale and in places like the Moho tenements in Queensland, we're looking at their regional groundwater, but then we're comparing it to either other sites where we've studied, different mineral systems and how that signature matches up. And so we look for similarities in that geochemical space mainly, but we are stretching out into looking at isotopes. There's not that many samples with isotope analysis for groundwater in Australia. So we're doing sulfur isotopes, deuterium and oxygen as well with this groundwater, as well as the standard sort of geochemistry. And that's really showing some interesting signatures at other sites, and we expect it'll transfer over into this area as well.
Okay.
And we're able to compare that to the state databases. So a lot of states collected routine groundwater, and so there's about 900,000 data points across Australia, and it doesn't have things that we're probably most interested in, gold, nickel, copper. But we're able to use a lot of those parameters also to understand the background and then infer, what a mineral system does to the groundwater chemistry.
On the theory side of things, also practical is what you're sort of comparing with your peers at the moment. But on the theory side, the idea is that the water travels through the rock, carries the elements which you are analysing, and if you were the water you're expecting to travel through mineralisation, or are you talking about what comes up from below?
So it's mainly there's potential to pick up hydrothermal fluid signatures for deeper groundwaters perhaps, but it's more about that interaction and the slow weathering of things at that rock into the sediment sort of interface that we're looking for. And these signatures are very subtle. I mean, with gold, for example, an anomalous signature might be 5 to 10 parts per trillion in that groundwater. So that's like a drop of blood in an Olympic-sized swimming pool. That sort of is or a couple of drops of blood for the anomaly, and we're able to detect that. And so, it's really subtle signatures in many cases, but because of the amount of broad data that we have to work from now, things like these more detailed studies in areas of interest are much more. We're much more able to interpret them better than we were in the past.
Is it an advance in interpretation, or is it advance in detection? Because analysing bore water is not new.
No.
Yeah.
It's a combination of both. I think we've got better in terms of the analysis side of things. So getting to those parts per trillion sort of levels of detection is advancing with the instrumentation and the technology. That's not just. We do a few pre-concentration steps in CSIRO, and we've kind of developed one technique for activated carbon for the PGEs and gold in particular. But a lot of it's the external labs are also developing the technology to do better analysis. So I think there's a combination of that. But then I think probably our major change was drawing on the major element chemistry and using that to interpret mineral systems, which we hadn't done before. We didn't think things like calcium, magnesium, sodium ratios in groundwater would be really interesting. And what we're finding is when we look at those on such a large data set, particularly in mineral systems, things like a chloride to sulfate ratio or something can really shift from a standard background. We use seawater, we plot seawater dilution and enrichment sort of curves, and it's the points that sit outside of that standard trend that really show up as being interesting. And sometimes they're either quite enriched, and sometimes they're quite depleted depending on where you are in the groundwater profile and a range of other things. But so that's a change in the way we interpret data. So in the past, we probably just focused on, if we're looking for nickel or gold, we were just looking at the nickel signature or looking at the gold chemistry. But now we're looking at a range of different parameters, and I think that's been the big change over the last probably 5 to 10 years.
Because CSIRO, basically the regolith is the weathering profile where it is. You guys been on this for decades. I remember when on my uni days, which is long time ago, you were already at the forefront of this kind of stuff, right?
Yeah, so I think a lot of the guys in CSIRO in particular, and some other organisations around Australia and in the world, pioneered a lot of the regolith type exploration in the 80s and 90s. Primarily, was a big boom for that, particularly gold and calcrete and things like that. And we sort of have had a bit of a lag, I'd say, over the last, I think probably the last 20 years, where we really haven't made big incremental changes in the way we explore. Hydrogeochemistry is increased, I think. Biogeochemistry is sort of wavered in its uptake and use. And we've spent a lot of time working on actually understanding how metals migrate through cover. So I think a lot of the time prior, it was just, let's detect things near the surface and do they match up? And probably the mid 2000s, we spent the better part of about 8 to 10 years working on how do metals actually migrate up through the cover and what stops them also, because that's an important learning for industry. It's not only saying yes, this will work, but it's also telling people no, there's areas that it won't work, and this is why. And so for the Moho example, I've been very keen on ultrafine soils as well as a technique, and that was one of the discussions early on, was like we actually don't think it will work in that setting just because of your cover thickness. So it's integrating a whole range of that regolith geoscience over the decades. It's been really important for us. I think we're at a point now where we're starting to make some different decisions and really integrate other data. I think that's the big change that I've seen probably in the last 3 or 4 years in particular, where everyone's talking about data integration, but it's taking your geochemistry, it's taking your geophysics, hydrogeochemistry, and it's merging it with spatial data sets, satellites, imagery, all sorts of things, and seeing if you can infer better signatures that way. And I think the machine learning sort of driver around that has really, that's our next step change, I think, for a lot of mineral exploration in the regolith world.
I mean, when we talk regolith, obviously rating profile means in situ. There's been a lot of talk about people analysing alluvials or transported things and being able to detect regolith chemistry. What's your thoughts on that?
Yeah, and I think it works in some settings and it doesn't work in others. And I think we have to be realistic. And I think in the past, people have oversold some of the geochemical techniques, especially, I would say. And I think we just have to be more realistic. Geochemistry probably works in some settings 5 to 30, maybe up 50 metres of cover, if you have understandings of why a geochemical signature might permeate up through that profile. So if you've got perched water tables that have sat there, redox fronts, things like this that could, essentially stew the geochem for a while and then let it dry out and it might move a little bit, or you've got multiple depositions with vegetation cycling that material, that's the way you might get a geochemical signature to the surface. Transported cover. But if you've just got a blanket dumping of, ignimbrites across in Chile or somewhere like that, there's no way the geochemistry is getting up through there. So I think we oversold some of the geochem approaches early on and saying this is new, it's novel, it's going to work everywhere, and I don't think it does. But in saying that, we've gone back to some of the fundamentals where we've done lab experiments and field experiments where we've buried ore. So we took Kalgoorlie super pit ore, for example, stuck it in little kid play pools and put 2 metres of sand on top of it and started measuring it. And what we found was that, where the water wasn't free draining through those holes, things would percolate. You get a little perched water over winter. We actually started detecting trace, 6 to 12 ppb gold above the gold ore over about 7 months. So it moves through 2 metres of sand cover pretty quickly. It's subtle, but we understood why it was doing that. Whereas the ones that we put some easily dissolved gold and lead salts and things like that, and they were nitrates, so they just dissolved really quickly, but they had holes drained in those kid pools, and the material just flew out float out the bottom, and so it was hitting the water table and going, it might make a good argument for why you would use hydrogeochemistry, but in terms of surface sampling there, it wasn't effective. So we kind of went back to a lot of the fundamentals and said, well, what would work and where? And is there reasons that you could explore through cover? And so I think we're quite confident that things do move up through the cover, but you have to be realistic about where it might work. And even in lab, we had little cylinders set up on columns with heat lamps to approximate essentially, I think it was about 30 years of Kalgoorlie sunlight to drive these sorts of evaporative sort of transpiration of metals, and we could get a nice zinc crust forming near the surface pretty quickly. But again, how that signature worked out was the zinc moved quite quickly, and this is these little experimental columns with sand and sulfide ore in the bottom. But down further in the column, things like copper was slowly coming up through that material, and things like lead and silver and bismuth weren't moving much at all. Like they'd only come up maybe a centimetre in that column. And using that in a field setting, what we're starting to think around is, if we were out in the Yilgarn or if we're out in North Queensland and looking for base metal targets, what you might be looking for is actually a zinc anomaly that's either really broad or completely almost dispersed, a tighter copper anomaly, and then things like lead, silver might be really point source anomalies. So it's integrating that understanding and experimentally derived understanding, and then putting that in a real world context that I think is changing the way we do our near surface exploration, and opening up opportunities.
Yeah. I mean, the techniques you're talking about is going to cost a lot less than some of the other old ways of trying to find things, which is important. In terms of hydrogeochemistry, in the terms of like what you guys are doing with Moho, how much movement is too much, or how do you factor that? Okay, I've got this signature of things from this well. How far could it have come from?
Yeah, I mean, in the Moho setting, we don't have a strong understanding of some of the Queensland environments. So this is why it's really important to do this study and sort of get a grasp of the size of the signatures. But in southern Queensland, where you've got a lot of like the Great Artesian Basin waters flowing, we haven't seen as and it's quite deep. We see bigger signatures, but not as clear cut. I think in the Moho areas, I think we're much better to get tighter signatures. In saying that, in the northern Yilgarn of WA, we see gold signatures on the order of 5 to 10 kilometres. So the major gold camps stand out. The Leonora, Agnew-Wiluna area all have these large gold signatures in the groundwater. The Sunrise Dam, Wallaby regions as well. Then for base metals, we see a tighter type of anomaly. So we might see it on the order of hundreds of metres to a kilometre or so. We don't see that really broad dispersion. But then on some of the when we're looking at base metal targets, what we're looking at with those, I've mentioned those major cations and anions at signatures. When we looked at that, I think it was about 1,500 samples across that area. When we looked at the Jaguar-Bentley VMS system, what we found was what we were looking for is a nitrate depletion or a sulfate enrichment, depending on which level of the groundwater you were on. And when we compared those samples across the whole of the northern Yilgarn, there was only one other area that had that same signature. It was within a couple of kilometres of the Quinns VMS deposit. So what we think is we're seeing signatures on that order if we interpret the data correctly. So maybe a few kilometres, and the bigger systems broadly on 5 to 10 kilometre scales.
So what you're saying, if you find something in this spot, it's either here or a couple of kilometres away? Yeah,
probably on that sort of order. Some of the other elements, things that you would, so things like copper and nickel, tend to get quite bound up in the clays and iron oxides quite quickly. So even though they might weather out of a sulfide, they don't move that far. So that's why it's really important to interpret a whole range of chemistry. And so with the Moho example, we are collecting about 60 elements and some isotopes and other things, and we'll look at those as a complete package. And the idea is that if you've got 50 to 100 kilometres of search space, maybe 10, 20 kilometres wide or something like that, you can get into a much tighter area quite quickly and economically. I mean, we're looking at in that area, maybe it's 100 odd samples, maybe maybe a little more depending on access, and we're at about $200 sample analysis for the whole lot. We're getting some pretty good information pretty quickly.
Yeah, I guess I think they've got a huge area. I think it was 1900 or something square kilometres, or it helps a lot.
Yeah. And that's really the idea of a lot of the techniques. It's not necessarily we're going to go out and say, here's your deposit right here, but it's making that first step to say, this is your most prospective area. This area is probably, you could get rid of that or put less effort in there, and making those decisions. And also we're incorporating things like probability and risk into those decisions as well. So some of the other work, not just with hydrogeochem, but with a range of data, is not putting uncertainty estimates on that. So where an area has been really well sampled, you have a pretty good degree of understanding of the uncertainty, so you can make a good decision to walk away from that area if it's not showing much. But there's other areas where you might only have a couple of samples, and the chemistry is quite varied, but we're actually able to produce maps of uncertainty where and easily viewed, people can say, oh well, if we walk away from that area, we walk away, but we only understand maybe 30 or 40% of the variation there. We either need to go back and resample, or we take that risk decision based on we accept that risk that we didn't quite sample that as effectively as we should have. So we're trying to put that sort of information back in front of the explorers, so that they can make those decisions not just on gut feel alone. People make good decisions on that end, but to be able to say, oh, I have a gut feeling that this is my better area, but then actually have a map that says, your uncertainty is poor here, you need to probably do more sampling, still could be a good area. That's an important sort of parameter.
I guess once they overlay geophysics over that, and it can, a 5-10 kilometre space could be reduced into much smaller.
Yeah.
And I think that's basically that's the key, right? It's trying to pinpoint your area of interest at the most efficient sort of means.
The biggest expense, and I'm not an active explorer, but I would assume is the drilling costs. Really, is getting drill rigs in is very expensive, and so what we're trying to do is minimise both for the economic footprint and also the environmental social responsibility too in terms of the drilling. So if we can minimise the amount of drilling for more effective exploration, then we're doing our job.
Yeah. Oh, look, fantastic. Look, guys who are watching, I mean, you can contact Ryan directly and ask him questions, or ask him through the video. I'm sure you got plenty of time to answer questions.
Yeah, certainly I'm happy to answer questions, and also feel free to get on the internet and search out stuff you're interested in. And if you find a CSIRO colleague or CSIRO person on LinkedIn, send them an email. We're very happy to talk to people, to go through our science. Or if you come to me and you have a different challenge, I'll redirect you to the right person that can sort of work with you. If it's geophysics, or if it's structural geology, or something completely different from my field, we'll get you into to talk to the right people. And there's a lot of programs, and Moho's a beneficiary of this as well, like government funding and incentives to work with researchers. And so not only are you putting some money back into research, but also benefiting your exploration, but you're also able to leverage government bodies as well to make your exploration more efficient, another level of efficiency. So there's a range of different opportunities with some of the state governments, and also we do a lot of things with the small medium enterprises with Innovation Connect projects, where essentially they almost can co-fund or match funding for research exploration.
Oh, look, CSIRO has been in this chasing regolith for 3 decades, probably plus 4 decades. So I was really excited to talk to Ryan, because I know this sector is where explorers live with, and if in some ways they can save money, all the better.
Yeah. And the challenge of exploring through cover is not going away. So we've just got to get better at it. We've got to accept it and work through it.
Yeah. All right, Ryan. Look, thank you for giving us time. Really appreciate that, and I'm hoping guys out there will get an appreciation of what this is all about. And like I said, feel free to ask us questions and leave comments, and contact Ryan directly at CSIRO.
Yeah, my pleasure.
Thank you.
Thanks for having me.